Light and your radio signal from the little box in your living room are the same thing. Identical. They are the same phenomenon, obeying the same laws, born of the same physics. And I can prove that to you in the next few minutes. But if that is true, and it is, then you have a real problem on your hands. Because one of them sails right through the walls of your house as if the walls were not there. And the other one, the light from the lamp in your kitchen, stops dead at the first wall it hits. Cannot get through. Not one bit. Same physics. Same laws. Different result. Somebody is lying to you. Or you have been thinking about walls wrong your entire life. Let me set this up properly so you see why it is disturbing. You turn on a lamp, you see the light. You walk into the next room, you close the door. Gone. No light gets through. The wall stops it cold. You have known this since you were 3 years old. It is one of the most obvious facts about the world. Walls block light. That is practically the definition of a wall. Meanwhile, there is a little radio transmitter somewhere in your house. It sends out a signal. That signal goes through the wall, through the door, through the ceiling if it has to. It reaches a device sitting on your desk in another room, on another floor, behind multiple layers of wood and plaster and paint. No problem at all. You do not think twice about this. But you should, you really should. Because those two things, the light from the lamp and the radio signal from that box, are traveling as electromagnetic waves. The same kind of wave. James Clerk Maxwell figured this out over 100 years ago, and it has never been wrong since. They are both disturbances in the electromagnetic field. They both travel at the speed of light. They both have an electric component and a magnetic component oscillating at right angles to each other. They are the same stuff. So what gives the wall the right to stop one and let the other through? I mean, really think about it. If someone had never seen either phenomenon and you described both to them, they would say you were contradicting yourself. You were telling me there is a kind of wave that travels at 186,000 miles per second, and when this wave hits a half-inch thick piece of drywall, it stops, completely absorbed. Not a trace gets through. And then you are telling me there is another kind of wave, the exact same type of physical phenomenon, same speed, same fundamental nature, and it goes through that wall like the wall is made of fog. They would say, pick one, either walls stop electromagnetic waves or they do not. You cannot have it both ways. But nature does have it both ways. And the reason is, one of the most beautiful things in all of physics, most people when they first hear this question come up with an answer pretty quickly. They say, well, the radio wave has a much longer wavelength, so it sort of goes around the wall, or it fits through gaps, or it is too big for the wall to notice. And the light wave is tiny, so it hits the atoms and gets stuck. That sounds reasonable. It sounds like it might be right. In fact, I have heard physics students say this with great confidence. And I want you to hold on to that idea for a few minutes, because it is the idea we are going to take apart. Here is the picture most people have in their heads. They imagine the wall is like a chain-link fence. The radio wave is like a big beach ball. You try to push a beach ball through a chain-link fence, it does not fit, it just smushes against it and bounces off. But wait, the radio wave gets through, so maybe the radio wave is more like a big ocean swell, and the chain-link fence is too small to interfere with it. The wave just rolls right over. Meanwhile, the light wave is like a marble, and the marble hits the chain links and stops. That is the mental picture, and I am telling you it is completely wrong. Not a little wrong, not mostly right, with a small correction needed. It is fundamentally wrong. It is thinking about the problem with the wrong machinery entirely. And once I show you why, you will understand something very deep about how light and matter actually talk to each other. Let me start by destroying the idea with a simple observation. If the chain-link fence theory were right, if it were just about size, about the wavelength fitting through the gaps between atoms, then you would predict a very specific thing. You would predict that anything with a wavelength bigger than the spaces between atoms in a wall should pass right through, and anything with a wavelength smaller than those spaces should be blocked. Fine, let us check that against reality. The atoms in a typical wall, say drywall or brick or wood, they are separated by distances on the order of a few angstroms. An angstrom is 1/10,000,000th of a meter, very, very small. The wavelength of visible light is a few hundred nanometers. That is a few thousand angstroms. The wavelength of light is already much, much bigger than the gaps between atoms. By the chain-link fence theory, light should sail right through. It is thousands of times larger than the spaces between atoms. If you are a wave, and the obstacles are thousands of times smaller than you, the fence model says you should not even notice them. But light does not get through the wall, so the size argument has a problem right from the start. It gets worse. X-rays have wavelengths that are much shorter than visible light, about the same size as the distance between atoms. In fact, 1 angstrom, give or take. According to the size model, X-rays should have a terrible time getting through walls. They are the same size as the gaps. They should be like a marble hitting a chain-link fence stopped cold. But what actually happens? X-rays go right through you, through your skin, through your muscle. They only slow down when they hit dense stuff like bone or lead. X-rays are shorter than light, and they get through more easily. That is the exact opposite of what the simple size theory predicts. So we have a situation where long radio waves get through walls. Very short X-rays also get through walls, but visible light, which sits right in the middle, gets stopped. Think about that. The stuff in the middle is blocked. The stuff on either side gets through. That is not a size story. Something else entirely is happening. And if you need one more nail in the coffin of the size theory, consider this. Take 2 walls. One is made of wood, one is made of glass. Same thickness, roughly similar atomic spacing, very similar density even. Light goes through the glass and stops at the wood. If it were about size, about wavelength versus gap, those 2 walls should behave identically. They are both solids, both full of atoms, packed tightly together, but one is transparent and one is opaque. The size theory cannot explain that. Not even close. Or consider water. Water is a liquid. Its molecules are constantly moving, sliding past each other. If anything, the gaps between molecules in water are larger and more variable than in a solid wall. And yet light goes right through water. You can see the bottom of a clear lake. You can see your hand through a glass of water. The molecules are loose, the spacing is generous, and light sails right through. Meanwhile, that solid wall with its atoms locked rigidly in place blocks every photon. The geometry is almost the opposite of what you would expect from the size argument. The tightly packed solid should be harder to get through if it were about physical gaps. But it is the tightly packed solid wall that blocks light, while the loosely arranged liquid lets it through. There is no saving the chain-link fence theory. It is dead. We need something better. Let me tell you what is actually going on. And this is the beautiful part. The wall is not a passive barrier. The wall is not just sitting there like a fence. The wall is an active participant in this interaction. The wall is made of atoms, and those atoms have electrons, and those electrons are the whole story. Everything depends on what those electrons can and cannot do when a wave hits them. An electron in an atom is not free to do whatever it wants. It is bound. It sits in what we call an energy level. You can think of it roughly like a ball sitting on a specific step of a staircase. The ball can be on the first step or the second step or the 5th step, but it cannot hover between steps. The steps have definite heights, definite energy differences between them. To move an electron from one step to a higher step, you have to give it exactly the right amount of energy. Not roughly the right amount, exactly the right amount. Now, here is the key. A photon of light carries energy, and the amount of energy it carries is directly tied to its frequency. Higher frequency means higher energy. Lower frequency means lower energy. This is one of the great discoveries of 20th century physics. Max Planck proposed it. Einstein made it concrete with the photoelectric effect, and it has been confirmed in every experiment since. The energy of a photon equals Planck's constant times the frequency. E equals h times f. That is the rule. So when an electromagnetic wave hits a wall, it is sending photons at the atoms in the wall. Each photon carries a specific amount of energy determined by the frequency of the wave. The question then becomes, does that particular amount of energy match any of the jumps available to the electrons in the wall's atoms? If the energy matches, if the photon's energy corresponds to the gap between one electron energy level and another, the electron can absorb the photon. It jumps up to the higher level. The photon is gone. Its energy has been swallowed by the atom. The light does not get through. If the energy does not match any available jump, the electron cannot absorb the photon. It has no way to accept that energy. The photon passes through. The material is transparent to that frequency. That is the whole story. That is everything. The wall is not blocking light because light is the wrong size. The wall is blocking light because By a coincidence of atomic structure, the electrons in drywall and wood and brick happen to have energy level gaps that match the energy of visible light photons. Let me give you an analogy that I think captures this perfectly. Imagine you are at a music hall, and on stage there are 100 tuning forks, all tuned to different notes. You walk in and you sing a note. If your note matches one of those tuning forks, that fork starts ringing. It absorbs the energy of your voice. The sound does not make it past the stage. The fork catches it. But if you sing a note that none of the forks are tuned to, nothing resonates. Your voice passes right through the hall, reflects off the back wall, comes right back. The hall might as well have been empty. The wall full of atoms is the stage full of tuning forks. The photon is the singer, and whether the song gets through depends entirely on whether any fork in the hall is tuned to that note. Visible light photons are singing the exact note that the electron tuning forks in drywall are tuned to. Radio photons are singing so low that none of the forks respond. It is a resonance phenomenon, not a size phenomenon. And let me say that again because it is important. It is a coincidence. There is nothing fundamental about walls blocking light. If the atoms in your walls were different, if they had different energy level spacings, light would go right through. And in fact, you know, a material like that, it is called glass. Glass is made of atoms. It is solid. It is a wall, if you want it to be. But light passes through glass beautifully. Why? Because the electrons in the silicon dioxide molecules that make up glass do not have energy level gaps that match visible light photons. The photons arrive, and the electrons have nowhere to put that energy, so the photons pass right through. Glass is transparent to light, not because it has holes in it, not because it is thin, not because of any geometric property at all. It is transparent because its electrons cannot eat visible light photons. They are on the wrong steps of the staircase. But now I want to hit you with the next surprise. Glass blocks ultraviolet light. You cannot get a sunburn through a window. Most of the ultraviolet coming from the sun gets stopped by the glass. Why? Because ultraviolet photons have higher energy than visible light photons, and that higher energy does match some of the energy level gaps in glass. The electrons in glass can absorb ultraviolet. They can eat those photons. So ultraviolet gets blocked, and visible light sails through. Same material, different frequencies, different outcomes. This is not a size story. This is an energy matching story. Think about what this means for a moment. A window is a wall for ants doing their ultraviolet dances, and a clear opening for you and me. A moth that sees an ultraviolet looks at a window and sees something opaque, like you look at a brick wall. Same window, different experience. Who is right? Both of them. Neither of them. The window does not have an intrinsic property of being transparent or opaque. It depends on who is looking and what frequency they are looking with. Now here is something that might puzzle you. If the story is all about electron energy levels, and the electron energy levels are determined by what atoms the material is made of, then how come glass and sand look so different? They are both made of silicon and oxygen. Sand is opaque and gritty. Glass is perfectly transparent. Same atoms. How can the same atoms produce different electron energy levels? The answer is structure. In sand, you have tiny crystals of silicon dioxide, each one a miniature ordered arrangement of atoms. But the grains are small, they have rough surfaces, and they scatter light in every direction. The photons bounce around between the grain surfaces and never make it through. In glass, those same silicon and oxygen atoms are arranged in a smooth, amorphous, non-crystalline structure. No grain boundaries, no rough surfaces. The electrons have the same energy levels, but the photons can travel through without being scattered off of tiny crystal faces. So it is not just about absorption. Scattering matters too, and scattering depends on the physical structure of the material at the scale of the wavelength. This is a subtlety worth mentioning because it shows that the full picture is richer than any one explanation. Absorption by electron energy levels is the main reason walls block light. But scattering off of structural features, reflection from surfaces, diffraction around edges, all of these play supporting roles. Physics gives you a toolbox, not a single wrench. Let me come back to the radio wave. Your radio signal from the box in the living room is oscillating at about 2.4 billion times per second. That is the frequency, 2.4 gigahertz. Now, what energy does that correspond to? Tiny, incredibly tiny, We are talking about a photon energy of roughly 100,000th of an electron volt. Compare that to a visible light photon, which carries about 2 electron volts of energy. The radio photon has literally 100,000 times less energy than a visible light photon. That amount of energy is far too small to match any electron transition in any normal solid material. The electrons in your wall simply cannot absorb such a pitiful amount of energy. There is no jump that small available to them. The lowest step on the staircase is already much higher than what the radio photon is offering. So the photon slides right through. The wall is transparent to it for the same fundamental reason that glass is transparent to visible light. The electrons have no way to grab the energy. To put some numbers on it so you feel the scale, the energy needed to jump an electron across a typical gap in a solid is somewhere between 1 and 5 electron volts. That is the visible light range. The energy of a radio photon at 2.4 billion cycles per second is about 100,000th of an electron volt. That is not even close. It is like offering someone a grain of sand and asking them to jump a flight of stairs with it. The currency is the same. Energy is energy. But the denomination is absurdly wrong. Even molecular vibrations, which involve whole groups of atoms rocking back and forth rather than electrons jumping between levels, require energies in the infrared range. That is still thousands of times more energy than a radio photon carries. The radio photon simply has nothing to offer. No atomic process, no electronic transition, no molecular vibration in your wall can make use of such a small packet of energy, and so the wall ignores it. This is why your radio signal goes through wood, through drywall, through plaster, through brick to some extent. The atoms in all of these materials have electron transitions at energies that simply do not overlap with the energy of radio frequency photons. But notice something. I said to some extent for brick, and if you have ever tried to get a signal through a thick concrete wall, you know it weakens considerably. Even if the electrons are not absorbing the photons directly in the staircase sense, there are other things going on. The oscillating electric field of the wave can push the electrons around a tiny bit, making them vibrate. Those vibrating electrons re-emit some radiation, which can interfere with the original wave. In some materials, particularly thick or dense ones, enough of this scattering and re-emission happens that the signal gets noticeably weaker. It is not the same as absorption. The wall is not eating the photons, but it is jostling them around enough to cause trouble. And this brings me to something I want you to notice. The answer to our original question is not simple. Though it is not one thing. Multiple phenomena are at work: absorption, scattering, reflection, and diffraction. And which one dominates depends on the frequency, the material, and the geometry. Physics does not give you one neat answer to every question. It gives you the machinery to figure out each specific case. And the machinery is the interaction between photons and electrons. Let me take you to the other end of the spectrum for a moment. Gamma rays. Incredibly high energy photons. Energies of millions of electron volts. What happens when a gamma ray hits your wall? It goes right through. Most of the time it barely notices the wall is there. But gamma rays do not go through because they are too small to hit anything. They go through because they are too energetic for the electron transitions in ordinary matter. The electrons in the wall have no jump big enough to absorb a gamma ray photon in a single step. The gamma ray is offering too much energy and the electrons cannot take it. So it plows right through. Although I should say, if the gamma ray hits a nucleus, that is a different story. Nuclear energy levels are very high, and gamma rays can interact there. And if the material is dense enough and thick enough, lead, for instance, even gamma rays get stopped eventually because there are enough atoms to provide enough chances for interaction. But in your house wall, gamma rays laugh at it. So the pattern is this. Very low energy photons, radio waves, pass through because their energy is too small for the electrons to absorb. Very high energy photons, gamma rays, pass through because their energy is too large for the electron transitions. Visible light sitting right in the middle range happens to match the electron transitions in common solid materials, and so it gets absorbed. The middle of the spectrum is the vulnerable spot. Is that not strange? The thing you see with the narrow band of electromagnetic radiation your eyes detect happens to be exactly the type that ordinary matter is best at absorbing. Or maybe it is not a coincidence at all. Maybe your eyes evolved to detect the radiation that interacts most strongly with the matter around you. The stuff that bounces off objects, that reflects, that scatters, that gives you information about surfaces and colors, that is exactly the stuff in the visible range. If your eyes detected radio waves, everything would look transparent. You would see through walls, through people, through furniture, useless for navigating the world. If your eyes detected gamma rays, almost everything would be transparent, except the densest metals. Also not very helpful for finding your dinner. Evolution tuned your eyeballs to the exact range where matter is interesting, where it absorbs and reflects and scatters enough to reveal its shape and composition. That is a beautiful thought, but I want to go deeper. Because so far I have told you the what, but I have not really told you the how. How does a photon actually interact with an electron? What is the mechanism? This is where we get into the part of physics I am most fascinated by. The theory of quantum electrodynamics, QED. I have called it the jewel of physics, and I stand by that. QED gives us the rules for how light and matter interact at the most fundamental level. In QED there are only three basic things that can happen. A photon can go from one place to another. An electron can go from one place to another. And an electron can absorb or emit a photon. That is it. That is the entire story. Everything in electrodynamics, every phenomenon you have ever seen involving light, from the color of a sunset to the reflectivity of a mirror, to why your radio signal gets through the bedroom wall, all of it comes from those three basic actions combined in various ways. The way we calculate things in QED is by considering all the possible ways something can happen. Not the most likely way, all the ways. You add up the contributions from every possible path, every possible sequence of photon emissions and absorptions. And the ones that contribute the most are the ones where the probability amplitudes add up constructively. The ones that cancel each other out, you never see them. When light hits a surface, for instance, it is not that the photon arrives, bounces, and leaves. Every photon explores every possible path, reflects off every possible point on the surface, penetrates to every possible depth, and the total probability of seeing the photon go in any particular direction is the result of adding up all those amplitudes. Most of them cancel. The ones that survive give you the classical law of reflection. Angle of incidence equals angle of reflection. But it comes from the quantum calculation, from adding up amplitudes over all possible paths. This is what makes QED so powerful and so unsettling at the same time. The photon does not decide to bounce off a mirror or go through a window. The photon explores every possibility simultaneously. The outcome we observe, reflection or transmission, is the result of a grand sum over all possibilities. And whether that sum lands on reflection or transmission depends on the quantum structure of the material, the energy levels of its electrons, and the frequency of the photon. When a photon arrives at the wall, it encounters an enormous number of electrons. Each photon has some probability of being absorbed by an electron, and that probability depends on whether the photon's energy matches an available transition. If the match is good, the probability is high. The photon gets absorbed. If the match is poor, the probability is very low. The photon continues on its way. But let me be a little more precise about what match means. But it is not like a key and a lock where it either fits perfectly or does not fit at all. There is a range, a width to each transition. We call it the light wave. An electron transition is not an infinitely sharp energy. It is spread out a little. This means a photon does not need to have exactly the right energy. It just needs to be close enough to fall within that light frame. The closer to the center of the transition, the stronger the absorption. Now for visible light and typical wall materials, the match is very good. The photon energies overlap strongly with the electron transition energies. Almost every photon gets absorbed within a very short distance of entering the material. The wall might be 5 centimeters thick, 10 centimeters, whatever. The light does not make it even a tiny fraction of a millimeter into the wall material before it is absorbed. For radio frequencies, the mismatch is enormous. The photon energies are so far from any transition that the absorption probability per atom is effectively zero. A radio photon can travel through many meters of ordinary building material and barely lose any energy at all. Let me give you a different angle on this. Think about what the electromagnetic wave is doing as it enters a material. The oscillating electric field pushes on the electrons. All of them, every single electron in the material, feels the push. Each electron starts to oscillate at the frequency of the incoming wave. If that frequency matches a natural resonance frequency of the electron, The response is enormous. The electron oscillates wildly. It absorbs energy from the wave. It is like pushing a swing. If you push at the natural frequency of the swing goes higher and higher. Push at the wrong frequency, and nothing much happens. The natural resonance frequencies of electrons in atoms correspond to the energy level gaps I was talking about before. For most solid materials, those resonances fall in the visible and ultraviolet range. This is why most solids are opaque to visible light. The electrons resonate at those frequencies and absorb the energy. At radio frequencies, you are pushing the swing at completely the wrong rate. The electrons barely respond. The energy passes through. At X-ray frequencies, you are pushing so fast that the electrons cannot keep up. They are too heavy, too sluggish, compared to the rate at which the field is oscillating. The X-ray goes through because the electrons cannot respond quickly enough to absorb it. Do you see? Too slow, too fast, and just right. It is like a Goldilocks principle. The electrons in your wall respond most strongly to light in the visible range. That is the frequency where the interaction is strongest. Below that range, the response drops off. Above that range, it drops off again. The peak absorption is right in the middle. I should tell you something about where the numbers come from, because it is quite remarkable. Planck's constant, the fundamental number that links a photon's frequency to its energy, has a specific value. 6.62, 6 times 10 to the minus 34 joule seconds. It is an extremely tiny number, and the charge of the electron is 1.6 times 10 to the minus 19 coulombs, also tiny. But when you work out the energies of electron transitions in atoms, using the rules of quantum mechanics, you get numbers that happen to fall in the range of a few electron volts. And a few electron volts corresponds, through Planck's relation, to frequencies in the hundreds of trillions of cycles per second, which is the frequency of visible light. None of this was designed. Nobody arranged it. It falls out of the mathematics. The fundamental constants of nature determine the structure of atoms, which determines the energy gaps, which determines what frequencies of light interact most strongly with matter. It is an unbroken chain from the deepest constants of physics to the fact that you cannot see through your bedroom wall. I find that breathtaking. This has consequences that go far beyond your house. The entire way we understand materials, the way we build telescopes, the way we design fiber optic cables, the way we make sunglasses, all of it rests on this principle. Every material has its own set of electron transitions, its own absorption spectrum, and that spectrum tells you which frequencies of light will get through and which will not. Water, for example. Water is transparent to visible light. You can see the bottom of a swimming pool, but water is very good at absorbing infrared radiation. That is why infrared does not penetrate the ocean very deeply. It gets absorbed in the first few meters, and water also absorbs ultraviolet, some wavelengths better than others. The ocean is transparent to a narrow window of the electromagnetic spectrum, visible light, just like your wall is transparent to radio waves, but not visible light. And if you go deep enough, even visible light gets absorbed by water. The blue component penetrates the farthest, which is why the deep ocean looks blue and why everything below about 200 meters is in perpetual darkness. Red light gets absorbed first within the first 10 or 20 meters. Orange goes next, then yellow, then green. Blue hangs on the longest. Each color, each frequency has its own absorption rate in water. It is not one number, it is a whole spectrum of absorption probabilities determined by the molecular structure of H2O. The atmosphere works the same way. The air above you is transparent to visible light and to certain bands of radio waves. We call those the optical window and the radio window. But the atmosphere blocks most ultraviolet, which is why you can survive outside without being fried by solar radiation. It blocks most infrared at specific wavelengths, which is connected to the greenhouse effect. Molecules like carbon dioxide and water vapor in the atmosphere have rotational and vibrational energy levels, not just electronic ones, and those levels happen to match certain infrared frequencies. The infrared photons from the warm Earth get absorbed by these molecules, re-emitted in random directions, and effectively trapped. The same physics that explains why your wall blocks light also explains why the planet is warm enough to live on. It is the same story playing out at different scales with different molecules. Even the reason the sky is blue comes from this interaction between light and matter. The nitrogen and oxygen molecules in the atmosphere are much smaller than the wavelength of visible light. When sunlight hits them, the molecules scatter the light in all directions, but they scatter shorter wavelengths, blue and violet, much more strongly than longer wavelengths like red. This is called Rayleigh scattering, and the scattering strength goes as the fourth power of the frequency, meaning blue light with its higher frequency gets scattered roughly 16 times more than red light. That scattered blue light comes at you from every direction in the sky. Hence blue sky. Sunsets are red because the sunlight travels through more atmosphere at the horizon, and by the time it reaches you, most of the blue has been scattered away. Only the red survives. All of this, every bit of it, is the same physics. Photons interacting with electrons and molecules. The frequency of the photon compared to the natural frequencies of the material, that is the only thing that matters. Every material in the universe is an electromagnetic filter. It lets some frequencies through and blocks others. And the filter is determined entirely by the quantum mechanical structure of the electrons in that material. Let me come back to metals for a moment, because metals are a special and interesting case. If you wrap your radio transmitter in aluminum foil, the signal gets blocked. Even radio waves with their tiny photon energies cannot get through a good conductor. Why not? I just told you radio frequencies are too low to excite electron transitions. What is going on? Metals are different. In a metal, the outermost electrons are not bound to individual atoms. They are free. They roam around the entire chunk of metal like a gas. We call them conduction electrons. Because these electrons are free, they can respond to any frequency, no matter how low. When a radio wave hits a sheet of metal, the free electrons slosh around in response to the oscillating electric field. They oscillate at whatever frequency the wave has, and when they oscillate, they re-emit electromagnetic radiation. That re-emitted radiation cancels the incoming wave on the far side of the metal. The wave gets reflected, not absorbed in the staircase sense, but reflected. The free electrons act like a mirror for all frequencies from radio up through visible light and beyond. That is why a metal box blocks radio signals. The technical name is a Faraday cage after Michael Faraday, who figured this out. It is also why metals are shiny. The same free electrons that reflect radio waves also reflect visible light. When visible light hits a smooth metal surface, the free electrons oscillate and re-emit the light right back at you. You see a reflection, a mirror. And notice a mirror is not reflecting light because it is smooth. Smoothness helps. Yes, it prevents scattering, but the actual reflection happens because of the free electrons. Polish a piece of wood as smooth as you like, and it will never be a mirror. It will still absorb the light. You need the free electrons. You need a material where the conduction electrons can slosh freely in response to any incoming frequency. Here is a thing that might surprise you. Your microwave oven uses this principle. The door of a microwave oven has a metal mesh embedded in the glass. A mesh with small holes. The microwave radiation inside the oven has a wavelength of about 12 centimeters. The holes in the mesh are much smaller than that, maybe a millimeter or two across. The microwave radiation trying to get through those holes finds that the free electrons in the metal mesh can respond to its frequency and reflect it back, so the microwaves stay inside the oven. But visible light with its tiny wavelength of a few hundred nanometers passes through the holes easily because the holes are much larger than the wavelength. That is why you can see your food cooking through the door. The mesh is a wall for microwaves and a window for light, the exact opposite of your house wall. Is that not wonderful? The same physics, reversed. In your house wall, the material blocks light and passes radio. In the microwave oven door, the material blocks microwaves and passes light. And in both cases, the explanation comes down to how the electrons in the material respond to the frequency of the incoming wave. But even metals have a limit. Push the frequency high enough up into the ultraviolet and beyond, and eventually the free electrons cannot respond fast enough. The wave gets through. Thin metal films become transparent to ultraviolet and X-rays. Even the free electron gas has a maximum frequency it can follow, called the plasma frequency. Above that frequency, the metal becomes transparent. Everything in this picture comes down to one question. Can the electrons in the material respond to the photon's frequency? If yes, the wave gets absorbed or reflected. If no, the wave passes through. The wall has no opinion about the wavelength in some abstract geometric sense. The wall responds through its electrons, and those electrons have very specific tastes. I want to pause here because I realize I have just laid out a pretty radical shift in thinking. Most people, before they learn this, think of the wall as a barrier, a physical obstacle that waves have to get through, like a ball rolling through a maze. Big waves squeeze through or roll over. Small waves get stuck. It is a purely geometric picture. The real picture is nothing like that. And the wall is a collection of quantum mechanical oscillators, electrons in their energy states, and the incoming photon is essentially asking each oscillator, can you accept my energy? If the answer is no, the photon proceeds as if the wall were empty space. If the answer is yes, the photon is gone. It is a conversation between the photon and the electrons, not a collision between a wave and a fence. And this is how I think physics should be taught, by the way. So that not here is the rule, memorize it, but here is a thing you thought was obvious, and I am going to show you it is nothing of the kind. When you break the obvious assumption and rebuild from the real physics, you learn something you never forget. If I just told you the answer, that walls block visible light because of electron energy level absorption, you would nod and move on and forget it by next week. But if I first make you believe in the chain-link fence model, and then destroy it piece by piece with counterexamples, and then build the real answer from the ground up, you own it. It is yours. That is the difference between being told a fact and understanding physics. This is why I love physics. The obvious answer, the intuitive answer, the one that seems so reasonable that you barely think to question it, turns out to be completely wrong. And the real answer is far more interesting. The real answer tells you that a wall is not a wall in any absolute sense. A wall is a frequency-dependent filter. Something can be a wall for light and empty air for radio, or a wall for ultraviolet and a window for visible light, like glass. The universe does not have walls and windows as fundamental categories. It has atoms with electron structures, and whether something is a wall or a window depends on who is asking. A visible light photon and a radio photon have very different experiences walking into the same room. Here is one more thing I want to leave you with, something that I find genuinely astonishing. We have this whole range of electromagnetic radiation. Radio waves at one end, gamma rays at the other, wavelengths ranging from kilometers to trillionths of a meter, a spectrum spanning about 20 orders of magnitude in wavelength, and your eyes detect a tiny sliver of it, a tiny band between about 400 nanometers, well, between about 400 billionths of a meter and 700 billionths of a meter, just a factor of 2 out of 20 orders of magnitude. But that tiny sliver happens to be the exact range where the electrons in common materials are most active, where atoms absorb and reflect most strongly, where the interaction between light and matter is richest, the range where you get colors, where surfaces have texture, where you can distinguish a rock from a puddle, a leaf from a branch, a face from a shadow. You did not choose this. Evolution chose it for you. For you, billions of years of natural selection tuned your photoreceptors to the band where the electromagnetic interaction with matter is most informative. And the whole reason that band is informative is quantum mechanics. The energy levels of electrons in the common elements, carbon, oxygen, silicon, nitrogen, the stuff the world is made of, those energy levels happen to have gaps that correspond to photons in the visible range. If the fundamental constants of the universe were slightly different, if Planck's constant were different, or the charge of the electron were different, those energy levels would shift, and the interesting band would be somewhere else, maybe in the infrared, maybe in the ultraviolet. And evolution would have given you eyes that see in that range instead. So the fact that light does not go through your wall and your radio signal does is not just a quirky fact about walls. It is a window into the quantum structure of matter. It tells you that atoms have discrete energy levels. It tells you that photons carry energy proportional to their frequency. It tells you that the interaction between light and matter is not a mechanical collision but a resonance, a matching game between the photon's energy and the electron's available states. Maxwell figured out that light was an electromagnetic wave. Planck figured out that the energy comes in packets. Bohr figured out that electrons sit in discrete levels. Einstein showed that photons are real. Put all of that together and you understand why your wall does what it does. 100 years of the greatest physics ever done, and the whole thing is sitting right there in the difference between turning on a lamp and getting a radio signal in the next room. You know, I sometimes think about what Maxwell would say if he could see what became of his equations. He wrote down 4 mathematical statements in the 1860s that unified electricity, magnetism, and light. He showed they were all the same phenomenon, but he lived in a world of gas lamps and telegraph wires. He could not have imagined a little box in your living room radiating electromagnetic waves through your walls to carry information. He predicted those waves. He predicted they would travel at the speed of light. He even predicted they could be generated by oscillating electric charges. But between his equations and the device in your room, you need Planck, you need Einstein, you need Bohr, you need Dirac. You need a whole century of quantum physics to understand why the wave gets through the wall. That is the thing about fundamental physics. Each piece looks small. A constant here, an equation there, a quantum rule that seems merely mathematical. But lay them all end to end, and they explain the everyday world with such precision that it takes your breath away. The fact that you can get a signal through your wall while sitting in a lit room where the light stays put, that fact contains within it the atomic structure of matter, the quantum nature of radiation, the discreteness of energy levels, the resonance of electrons, and the entire theory of quantum electrodynamics. It is all there, packed into one ordinary moment that you never think about. The next time you walk from your kitchen to your bedroom and your radio signal follows you through the wall while the kitchen light stays behind, remember what is really happening. The electrons in that wall are catching every visible photon like a fielder catching baseballs, one after another. They are hungry for that energy. They have been waiting for exactly that frequency. But when the radio photons arrive, those same electrons do not even blink. They have no appetite for it. Too little energy, not on the menu. And so the radio wave passes through like a ghost through a crowd, present but untouched. That is not just an analogy. That is what is actually happening, described in the language of QED, the most precisely tested theory in all of science. Every photon, every electron, every interaction is governed by those rules. And you carry the proof of it in your pocket every day without thinking about it. So let me ask you this. Glass is transparent to visible light, but blocks ultraviolet. Your wall blocks visible light but passes radio. Metal blocks almost everything until you get to X-ray frequencies. Every material has its own electromagnetic personality, its own window of transparency and opacity. If you could design a material from scratch, atom by atom, picking the exact electron energy levels you wanted, what frequencies would you make it transparent to? And what would you use it for? I am genuinely curious what you come up with.